an equation, and let's check the arithmetic, make sure that we're on the same page, and then talk about what that means physiologically. This is not, I mean, plugging and doing the arithmetic is not the interesting thing. So, what's the clearance of sodium? 1.1 mils per minute of urine times the urine concentration, adjusted for the fact that this is mils and this is liters. Clearance. So we don't have to do that with clearance because this is milliequivalents per liter, this is milliequivalents per liter. We're in the same units here. Units cancel, so we get mils per minute and 0.39. So 0.39 mils per minute is the clearance of sodium. Why is it lower than the GFR? A lot lower. The GFR is 100 mils per minute, and the clearance of sodium is 0.39 mils per minute. Why is it so much lower? Renusha?
So for the urine concentration and the serum concentration, if you have the same unit, you don't have to change them in milliliters per minute.
You don't have to. For clearance. We will have to change it here.
Okay, because we still use 50 and 140, right?
Because they're in the same units.
Okay, I see.
I could turn them into mils, and I could divide this by 1,000 and this by 1,000, but I took a shortcut.
Yeah, but I'm wondering, the 1.1 is still in milliliters per minute, right?
This is milliliters per minute.
Okay, I see.
And so the answer is in milliliters per minute.
Makes sense.
Why is this number such a small fraction of GFR? Sophie?
Is it because the salt is reabsorbed?
Sodium is actively reabsorbed. We recover 99.6% of the filtered sodium. That's the answer. So here's the filtered load of sodium, 14 milliequivalents per minute. Here we did have to change from, because this is in mils per minute, and this is in milliequivalents per liter. So I had to make sure I converted that into mils. Any questions about this number? And here's the same calculation for the excreted load. Volume per minute of urine, urine concentration converted into concentration per milliliter. Why is this so much smaller than this? The same answer. Kate. Because we reabsorb it.
Where's the 1,000 coming from?
1,000 milliliters per liter. So this illustrates that we filter sodium, but we reabsorb 99.5% of it. And so very little of it ends up in our urine. We are specialized for conserving sodium. We evolved in a scenario where sodium was pretty hard to get. Sodium is not an abundant salt in most environments. We now live in an environment where sodium is easy to get. Open up a bag of chips and you get your daily need for sodium just by breathing it. I mean, not really, but I mean, we no longer live in a world where sodium is a precious commodity. But that's not the world we evolved in. We evolved in a world where sodium was precious, and we evolved a mechanism for conserving it. This can lead to a problem now in the world that we live in when we ingest so much sodium. That's a problem. It can lead to health problems. But that's not the problem, that's not the situation we evolved in. Some of you may know that the word salary, what we earn in pay, The word salary comes from salt, because there was a time when people were paid in little packets of salt, because it was that precious. So we evolved in a world where we conserve sodium by reabsorbing almost all of it. Okay, the urea. Urea is a, does anyone know where what urea is a product of?
Protein, like red meat.
It is definitely in red meat, but why do we have urea in our body? It is a product of nitrogen metabolism. So we eat protein. Protein has nitrogen. Protein, when we metabolize protein in our diet, it generates ammonia, but ammonia is toxic. So we have a mechanism for detoxifying ammonia and producing urea. Fish just urinate ammonia because they live in a world where the water just flushes it away. So fish just excrete ammonia. They don't convert it to urea. Birds convert their ammonia into uric acid, which makes that white paste in bird poop. Mammals convert their ammonia from protein diet into urea. You're going to see we use urea in the kidney to actually help make concentrated urine. But this is the urea. So this is the urea number that I got for the clearance. Why is the clearance of urea? What can you conclude about the clearance of urea compared to the clearance of sodium? What's your observation?
Like the urea is basically all excreted.
All, not all, because the clearance of urea is greater than the clearance of sodium, but it's not the GFR. We reabsorb some of it. We reabsorb a lot less of it than we reabsorb sodium, but we reabsorb some of it. If we didn't reabsorb some of it, then the clearance of urea would be equal to the GFR. But that's almost never the case.
Why do we reabsorb some of it? Like, what do you mean with?
Save that question for next week.
Is it DNA stuff?
Is it what?
Is it the nitrogen basis of DNA?
No, we don't reabsorb it for DNA synthesis. At least maybe we do for a biochemist, but for a physiologist, we reabsorb it to help make a concentrated urine when we are dehydrated. Okay, so now we're going to talk about a complicated concept whereby we regulate filtration, glomerular filtration. We control glomerular filtration. So you've learned a little bit about this already. You've learned that we can constrict the afferent arteriole, and that will lower GFR. You've learned that we can dilate the efferent arteriole, and that will lower GFR. We can constrict the efferent arteriole, and that will increase GFR, or we can dilate the afferent arteriole, and that will increase GFR, right? You've learned that principally. Now we're going to get into the mechanisms of that, and I'm going to simplify it. So we're going to talk about the sympathetic nervous system, and we're going to talk about the autoregulation by the juxtaglomerular cells and the macula densa. Those are the way we control it. We control it by the sympathetic nervous system and by the juxtaglomerular apparatus. The mechanisms are complicated, and in the past I have asked students to learn these mechanisms, and I'm going to simplify it for you, okay? So so some of this is simple. Some of this you already understand. The sympathetic nervous system, you already showed me that you understand how norepinephrine can affect through a GPCR, a GQ-coupled GPCR, how it can lead to constriction of the afferent arteriole right? So sympathetic nervous system, release of norepinephrine onto the smooth muscle cells of the afferent arteriole, constriction of the afferent arteriole, decrease in GFR. You know this already from the this is circling back to the cardiovascular section. Remember, I was standing right here when I told you that some beds, when we're stressed, some areas of our body get vasodilated, like our brain and our liver and our skeletal muscle. And some, when we're stressed, physiologically stressed, some areas of our body become vasoconstricted. Digestive system, kidney. Now we're coming back to that. We're seeing that the kidney decreases GFR when we are physiologically stressed by constricting the afferent arteriole. So this one you already know. This one I am not going to ask you to learn, okay? It's complicated, 7 weeks, too condensed. The point I do want you to know is that the fluid coming from in the distal tubule communicates with the macula densa. Remember, the macula densa is right next to the afferent arteriole, and there is a mechanism that I am not going to ask you to learn about, by which the flow of fluid in the distal tubule either down or up regulates the constriction of the afferent arteriole. Okay, so there's this whole mechanism. There's the macula densa, whole mechanism, there's the G protein. You don't have to know it. The point is that there is flow in the distal tubule that controls GFR through the cells of the macula densa and this juxtaglomerular apparatus. The purple and they're not purple, and the teal cells are the juxtaglomerular cells. So
is it, if there's a high flow, there's less GFR, or what
if there is high flow, so this is an auto-regulatory thing. If we have a lot of flow in the distal tubule, the kidney says, whoa, we've got a lot of flow, we're filtering too much. So let's shut down the filtering by decreasing GFR. So it's an auto-regulation mechanism. Does that make sense, auto-regulation? High flow, wait a second, maybe we're getting too high, let's slow it down. High flow decreases GFR, macula densa in the distal tubule plays the role. That's what you need to know. Do not focus on the neurotransmitter, the receptor, etc. Okay? Is that clear what I want you to know and what I don't want you to know? This is a case where on the fly I decided that this was too much. Go ahead.
The underlying curve on the bottom, the GIGO, is that the GO from olfactory?
No, this is GO is another name for GI.
Oh, okay.
This is not GOLF. And this is a weird GI because it's not coupled to adenyl. Some of it is coupled to adenyl cyclase and some of it acts like GQ. It gets weird. If there is low flow, then this same operation, so if there is low flow in the distal tubule, the macula densa detects that and activates the renin, angiotensin, aldosterone endocrine system. This is endocrinology. This is AMP1. So I am not going to ask you to learn renin angiotensin, but I will ask you next week to understand the mechanisms by which aldosterone has effects on the kidney. Okay? So the point here is that low flow, detected by the macula densa, tells the juxtaglomerular cells to release renin and activates this endocrine cascade. It's endocrine, that's AMP1. Put it aside, but we will talk about aldosterone next week, and this is where the aldosterone comes from. So this is an area where the two courses don't play very well together. Because in AMP1 we talk about this, but I don't explain the mechanisms of aldosterone. And in AMP2, I don't explain this, but we are going to understand the mechanisms of aldosterone. And so only if you take both courses and you take this information months apart do you understand the whole system. It's just the way it is. And finally, so we've talked about tubuloglomerular feedback, both for high flow and for low flow. We've talked about the renin-angiotensin aldosterone system. And finally, there is another system that controls GFR, and that is a hormone that is secreted by the cardiac atria. So your heart atria, in addition to being a muscle that contracts and pumps blood from the atria into the ventricles, also releases a hormone. It's called ANP, atrial natriuretic peptide. Atrial, from the atria. Natriuretic, let's unpack that one. Anyone know what Na might be referring to here? Sodium. The word in Latin for sodium is natrium. Natriuretic. What's uretic? In the urine. This is a hormone that helps us excrete sodium when we need to excrete sodium, if we happen to eat a lot of sodium. So there is, when we have stretch, again, you don't have to know the mechanisms. I do want you to know that there is this hormone called ANP that stimulates GFR and helps. Anything that increases GFR will allow the kidneys to excrete more sodium, because more sodium would be filtered. So now I have a decision to make. Let's do a clicker or two. Let's do a clicker. During osmosis alone, just osmosis, we're not talking about any hydrostatic pressure, we're talking only about osmosis and osmotic pressure. Which way does water flow? Okay, so this is a tricky one. So, is A a true state? Let's just go through this together. I don't mean it. Is A a true statement? I mean, A is a true statement in the sense that if there is hydrostatic pressure, solution will flow from a higher hydrostatic pressure to a lower hydrostatic pressure, but that's not an answer to the question, okay? From the solution with the higher solute concentration to the lower solute concentration. No, that's the opposite of what osmotic forces would produce. From the solution with the higher osmotic pressure to the solution with the lower osmotic pressure, the answer to that is yes. That's just the way it's expressed. So the solution with the lower concentration is the solution with the higher osmotic pressure. And from a dilute fluid to a concentrated fluid, yeah, that's it. So that's a correct answer. I mean, these two are the correct answers. I want you to understand osmosis and the definition of osmotic pressure. Let's do another one together. Which of the following would, individual or in combination, would cause a maximal glomerular filtration? So let's just do this together one at a time. Which of these would increase glomerular filtration? Constriction of the afferent arteriole? No. Dilation of the efferent arteriole? No. Dilation of the afferent? Yes. Constriction of the efferent? Yes. So maximal would be the both of them. Okay? Which of these would decrease? Which of these would decrease GFR? Let's do this one as an actual quick. I'll give you a chance to do it. Okay, good. I'm seeing a lot of correct answers. They all, any questions about why all of these are correct? So
Can you explain B?
D as in,
B?
B as in Baker?
Yeah.
Dehydration. So if we are dehydrated, let's just think about it sort of globally. If we're dehydrated, we want to conserve water. The first step to conserving water is not filtering it. So that's the global way to think about it. If we're dehydrated, we have a high concentration of solute in our blood because we have low amount of water. High concentration of solute would lead to more flow from Bowman space into blood, which would decrease glomerular filtration, because that's an opposing force. So the osmotic force would decrease, or would counteract the hydrostatic pressure more. Questions? Okay, so now I get to my decision point. Rather than go into the third lecture, well, rather than try to do the third lecture, which is important material and I'm not going to try to do it, what I want to do is set it up. So I would like to start it and I would ask you to bring your handout to class on Monday, but we will not try to do it. Okay, so let's go through some of it. Okay, we've already done most of this. What we're going to set up sodium and glucose reabsorption, but we're not going to do it. Okay, because it's too important to do 2.5 hours in. It's too important. So we're going to do it on Monday. That means I'm going to have to do it fast, and so I want to set it up. So let me just set it up. This is stuff we've done. So this is part of the setup. So this is information that I want you to hold on with me here, another 15, 20 minutes. get this information, take your notes, bring it with you on Monday. This will not be on the quiz. Everything up to this point is quizzable. After this is not quizzable. This is so that we can move fast on Monday. So, we filter a lot of water. 180 liters a day, which is, if you take the GFR, which is in mils per minute, and you multiply it times minutes per day, you get something like 180 liters per day. But we reabsorb 99% of it. We reabsorb about 99.5% of the sodium we filter. Unless we're sick, we reabsorb 100% of the glucose and some fraction of the urea. We want to get into the mechanisms of how the tubules do this. That's what I'm setting up. We're not going to get into the details today. I want to set up how the tubules, the proximal tubule, the distal tubule, and the loop of Henle do this. Reabsorb sodium, reabsorb glucose, reabsorb water, and we're also going to talk about bicarbonate and potassium. How do the tubules do that? How do the tubules do that? That's the important concept for next week. The setup is that I want to set up the anatomy of the tubules. The tubules, so this is an actual slide of a cross-section through the kidney. This is histology that we're going to be doing in lab this week. So you will learn some of this week, and that's another reason why we're getting this far. Do you think your kidneys are purple? Why is this purple? Stained. It was stained with a stain that stains the nuclei and stains the cell membranes. So these circles are cellular nuclei, and these cells are these square things. So here is a tubule. Here is a tubule in cross section. There's a lumen, there's a space outside, and there's a layer of cells that form the tubule. And I don't know if this is proximal, distal, or loop of Henle. At this level right now, we're talking about them all. All the tubules have a lumen, an outside, and a layer of cells. These cells form a barrier between the lumen and the outside. And they are epithelial cells. So this tubule is an epithelium. It's not an endothelium. What cells, endothelial cells, line what type of tube that you have heard about in this course? The what? Airway? Yes, we have endothelial cells inside the alveoli. We also have endothelial cells inside, we have type 1 and type 2 cells inside the alveoli. I'm not even sure. Inside the blood vessels, inside capillaries, we have endothelial cells. Endothelial cells line things like capillaries. Epithelial cells line things like the renal tubules, and they're real different, even though they sound similar. Epithelium. And we're going to talk about the membrane that is facing the lumen, which is called the apical membrane. The apical membrane is the membrane of these cells that faces the lumen of the tubule. That's this membrane. This membrane here of each of these cells is the apical membrane. The rest of it is called the basolateral membrane. Base, lateral, basolateral. Apical, basolateral. I want you to know these words because I'm going to start using them real fast next week. The lumen, the apical membrane faces the lumen, the basolateral membrane faces the outside. All of these blobs, what do you suppose these blobs are? What, in my world, all these blobs are always some kind of protein. And these are all going to be transport proteins. So we have transport mechanisms on the apical membrane, and we have transport mechanisms on the basolateral membrane. You're going to get into the thick of this next week. The apical membrane is almost always folded. So you can see here, this folding mechanism, folding here. We can't see it in this micrograph, but there's folds inside some of these tubules. This micrograph doesn't show it. So the lumen faces this folded apical membrane, and then the basolateral membrane is not very highly folded on the other side. The tubule, lined by the epithelial cells, surrounded by the capillary. The tubule, lumen, epithelium, membrane, very thin membrane to support it, and then capillary. We are going to talk about the mechanisms by which solute and water move from lumen into capillary during the process of reabsorption. We're going to talk about those molecular mechanisms. So what I want you to walk away with is the image of this epithelium and the apical and the basolateral membranes. Because we're going to get into things like, this is now what I don't want to do, but this is where we're going to go on Monday, to talk about the molecular mechanisms by which sodium is reabsorbed from lumen into capillary. It's important. And you know how I love molecular mechanisms, so I'm going to make you love it too, whether you like it or not. Okay? So that's what we're going to do next week, but that's why we're not going to do it today, because it's too important to try to squeeze into the end of a long day.